Let us take this first question. For an overhanging beam shown in figure, determine support reactions at A and B, draw SFD and BMD and find the point of contraflexure. Now this is the question which we have in front of us. Let us try to write the data first. Here I will draw the beam which is given. Now this is the question which we have in front of us, where we have an overhanging beam which is supported at point A at point B. Then we have point load of 10 kilonewton, 24 kilonewton and 15 kilonewton acting on this beam. For this diagram we have to find out the support reactions. The first question is, we have to calculate reaction at A and reaction at B. That is, I have to determine RA value and RB value. The next part is, we have to calculate SFD and BMD, and after that we have to find the point of contraflexure. So this is the question which we have. I'll write the solution for this. I'll say that for the equilibrium condition of the beam, that is my step number 1 is calculation of support reactions. Here I will say that for the equilibrium condition, first summation of Fy is equal to 0, where I will treat upward forces positive and downward forces negative. So therefore I have the sum of vertical forces as Ra is upward, Rb is upward, so both are positive. That is Ra plus Rb. 10, 24 and 15, they are downward, so negative. Minus 10, minus 24 and minus 15 is equal to 0. Therefore we have Ra plus Rb is equal to, if I add these terms, it will be 10 plus 24 plus 15, which is 49. Here I have negative 49. If I shift it onto the other sides, it becomes positive. So here I have my first equation. After this I will be taking moments at point A. So I'll say that summation of moments about point A is equal to 0, where clockwise moments are positive and anti-clockwise moments are negative. So therefore, if I am taking moment at point A, I start from RB, the moment is anti-clockwise and distance is 7 meter between point A and B, so it is minus RB into 7. Next, here I have 15 kilonewton, which is at a distance of 10 meters from point A and it is in clockwise direction, so I'll take it as plus 15 into 10. Then I have 24 kilonewton, which is at 4 meters from A and it is in clockwise direction, so plus 24 into 4. Next, I have 10, its distance is 2 meters from point A, and if I take the moment about point A, it is in anti-clockwise direction, so minus 10 into 2. Therefore, if I calculate all terms here, I will be getting RB as, it comes out to be 32.29 kilonewton, and after this I will say that put RB is equal to 32.29 kilonewton in equation 1. So therefore I have RA, it was plus RB, so plus 32.29 is equal to 49. Therefore RA is equal to 49 minus 32.29. Therefore, RA value, it comes out to be 16.71 kilonewton if I subtract these values. So here I have found out the support reactions, and this completes the first part, that is I have got the first answer, RA RB values. Now I will be writing the values here. RA is 16.71, RB is 32.29. So here I have found the support reactions. The next part is I have to calculate shear force. So my step number 2 is SF calculations, and for that I will draw the sign convention first. Upward force to left and downward force to the right are positive. Downward force to left and upward force to right, they are negative. So therefore I will start calculating the value of shear force. First I will be taking the section at, you can say, very close to point C. This is my section. I'll say that first SF at point C is equal to, here I have a section and to the left of it there is downward force. So downward force to the left is taken as negative, value is minus 10 kilonewton. Next, this shear force will remain constant between C to A up to left of A. Now when I take the section to the right of A, and if I look to the left of this section, I have minus 10 and plus 16.71. So SF at point A, minus 10 plus 16.71, that comes out to be plus 6.71 kilonewton. Now this value of shear force at point A will remain constant from A to D up to the left of D. If I take the section to the right of D, then I have minus 10 plus 16.71 minus 24. This value of shear force, it comes out to be minus 17.29 kilonewton. Next, SF at point B is equal to, if I take the section to the right of B, here I can calculate it in two different ways. Either I can see the left of section or right of the section, the answer will be same. So here if I take left, I'll have minus 10 plus 16.71 upward minus 24 downward plus 32.29 upward. So I have the value as plus 15 kilonewton, and this value will remain constant up to point E. So I say that SF at point E is equal to plus 15 kilonewton. So these are the SF calculations. Now I would be drawing the SF diagram. For that I have to draw the beam once again. So this overhanging beam, I will draw it again. This is the beam which is given, supported at A and B. Now I have to draw the shear force diagram. For that I will first be projecting the points downward. For drawing shear force diagram, the length of shear force diagram should be equal to the length of the beam. SF at point C, that is minus 10, so downward, (10 kilonewton). Now this 10 kilonewton will remain constant between C to A because there is no load between them. So here 10 kilonewton is constant. Next, at point A, the value is plus 6.71 kilonewton. So from negative it will go into positive. Here I have 6.71 kilonewton. Again this will be constant between A to D since there is no load between A to D. Then at point D, the shear force is minus 17.29. So from positive it again goes back to negative 17.29, and this will remain constant between D to B since there is no load between D to B. Next, at point B, the shear force is plus 15. So from negative again it will go into positive region, having value 15 kilonewton. So here is the shear force diagram which we have. I can write 10 here also, 10 kilonewton. This 6.71 kilonewton remains constant, so 6.71 kilonewton. Here I have 17.29 kilonewton and this 15 kilonewton is constant. Positive sign above the line, negative below the line. So this completes my shear force diagram. After completing shear force diagram, we will be going on to step number 3, that is bending moment calculations. Step number 3 is bending moment calculations. As we can see here we have an overhanging beam. So for overhanging beam, at the ends which are free, that is the end which is hanging at point C, at point E, the bending moment will be 0. So here I can write it as, first of all, moment at C is equal to moment at E, that is equal to 0. Into the bracket I can write down, since it is overhanging beam. After this, I will calculate the bending moment at point A, B and D. First, starting with point A, and just before the calculation I will draw the sign convention. Clockwise moment to left and anti-clockwise moment to the right are positive. Then anti-clockwise moment to the left and clockwise moment to the right are negative. So these are my sign conventions. Based on this we will find the bending moment. So starting from point A, if I see here, to the left of A I have only one force, that is 10 kilonewton, and it is producing moment in anti-clockwise direction. So if my section is at point A and this moment is in anti-clockwise direction, so anti-clockwise moment to the left is negative. So here I have moment at A is equal to, it is minus 10 into 2, because here I have minus 10 kilonewton downward and it is into 2 meter distance. So that is minus 20 kilonewton meter. Next, bending moment at point B. Moment at B is equal to, here if I take the section at B, to the right of that I have 15 kilonewton. producing clockwise moment. So clockwise moment to the right is negative. So here I have 15 into 3 with a negative sign, that is minus 45 kilonewton meter. After that, moment at point D. So for that I can take either the left or right section. So moment at D will be equal to, if I take the section at D, to the left of it 10 kilonewton is anti-clockwise, so it has to be taken negative. So 10 into 6, that is minus 10 multiplied by 6. Next I have here reaction at A, whose value is 16.71 kilonewton. RB is 32.29 kilonewton. Now if I see here, 16.71 kilonewton will produce clockwise moment to the left, so it is positive. So 16.71 into 4. Therefore I get bending moment at D is equal to 6.87 plus kilonewton meter. So here I have found the bending moment values at each of the points. With this we can draw the bending moment diagram. At the free end, first of all, here I will be drawing a straight line, because straight line indicates the length of the diagram. Bending moment at C and E, they are 0. So moment at C is 0. Moment at E is equal to 0 because they are overhanging beam. Now moment at A is minus 20. So moment at A would be in the downward direction, 20 kilonewton meter. I will write the sign afterwards. Next, moment at B is equal to minus 45. So at B it is again negative 45 kilonewton meter. I will write the sign. Then at D the bending moment is plus 6.87. At D it is plus 6.87 kilonewton meter. Now I have to join these lines. Wherever we are getting shear force as a straight constant line, bending moment is an inclined line. Between A to D, shear force was a straight line, so bending moment is an inclined line. Between D to B, it is again straight line, so bending moment is inclined. And between B to E, it is straight line, so bending moment is inclined. Positive and negative. Here we have completed the bending moment diagram. This is the BMD. Now as we see in the bending moment diagram, there are 2 points where bending moment is changing its sign, or you can say bending moment is 0 at these 2 points, and these points, they are called as point of contraflexure. So here I have 2 points as the point of contraflexure, as we can see. So we need to know the location of these points. I will start with the first point. I'll say that this point, the first where the bending moment is changing its sign, I'll say that this distance is x1. So now I will find how much is this distance x1, and then I will be calculating x2. So first for x1, I'll say that the step is step number 4. Location of point of contraflexure, and for that I will draw 2 similar triangles. First, the triangle having base x1 and the other one which has base, since 4 meter is the total length and from A I am taking distance as x1, so the remaining distance is 4 minus x1. So I will draw these 2 similar triangles. So here I have 2 similar triangles. From this I will say that if I take the height of first triangle, that is bigger triangle, upon the base of the bigger triangle is equal to height of smaller triangle upon base of smaller triangle. So therefore I have 20 into 4 minus x1 is equal to 6.87 x1, and here if I multiply that becomes 80 minus 20 x1 is equal to 6.87 x1, and therefore x1 value, if I calculate, I will be getting this as 2.8 meters. This 2.8 meter is from point A. So this is from point A. So I have located the first point of contraflexure. Next, I will locate the second point of contraflexure, and that is I locate it with respect to point B. I'll call this distance as x2, where the bending moment becomes 0, and again I'll say that by similarity of triangle, here I have a triangle whose base is x2, height is 45, and I have a smaller triangle whose base is, since this distance is 3, if I am taking x2 from B, this is point B, from this if I am taking x2, so the remaining distance is 3 minus x2, and the height here is 6.87 kilonewton meter. Now I'll say that again by similarity of triangles, if I take height of smaller triangle upon base of smaller triangle is equal to height of bigger triangle upon base of bigger triangle. So therefore here I have 6.87 x2 is equal to 45 into 3, 135 minus 45 x2. I will be bringing x2 term on one side, number on one side, and calculating this part. From this I will get my x2 value as it is 0.4 meters from point B. So as we can see in this problem, we had solved all three questions which they were asking. The first one, reaction at A, reaction at B, we have already calculated. SFD and BMD, we have completed the shear force diagram, bending moment diagram, and the last part was point of contraflexure. So here we have located the point of contraflexure, x1, the distance is 2.8 meters, and x2, the distance is 0.4 meters. And once we have located the point of contraflexure, we can say that the problem is completed.